Okay, back for the final installment here. I can't even remember where I left off. It was somewhere up here, I think, when the camera ran out of battery. But picking up at 26, this is a rational function. So, but we're just simply finding out when is it equal to 1. So I sub in for 1, and then I cross multiply, and I solve and factor, and I get the answer there. Okay, so that's the key thing, just to sub and cross multiply and solve. Now it says find the sum of the measures of the interior angles and the exterior angles. That's the sum of them for the polygons 5-sided, a 12-sided, and an n-sided. Well, you simply have pentagon with 3 triangles. Each of these is 180, so you're multiplying by 180. All right. On down to this one. I guess this is where I left off. Now it's coming back to me. We go backwards and solve. Oh yeah, and I was right here. Alright, well just pop that into your calculator and divide and add 2, and that's how many sides you're going to get. What is it going to be? It's going to be, I think, 17 sides? Try that out. Find each indicated measure, the sum of the measures of the interior angles of a decagon. Okay, so that's 10 sides. N equals 10. So you're just going to put it up into that formula, take away 2, 8 times 180, all right? Find the measure of each interior angles of a regular, of each individual one. So whatever this total is, you're going to divide by 10. Well, it's actually easier to start with this, because if you know you've got 360 degrees of exterior angles and you've got 10 vertices, that means each one is 36 degrees. So your each interior angle is going to be 180 minus 36, and that's 144 degrees. Okay, so that's pretty easy. Then, of course, if you got 10 of them, that does the math for you, and that would be 1440 degrees right there. Find the measure of each exterior angle of regular decagon. Well, that's what we found to start that problem. All right, so now very much the similar idea for these. These are all quite easy. When you have an exterior angle, you know there's 360 degrees in total. If there's one that's 30 degrees and they're all the same, that's going to give you 12 sides. Each interior angle is 160, so that means each exterior angle is 20. So we can do the same math here, divide 360 into our groups of 20, and we've got 18 sides. Given the figure below, this is isosceles, or these are equal chords. That means these are equal arcs. If this is 150, we subtract 150 from 360 and we divide by 2, and each one of these is 105 degrees. And then they're asking, this is the 3 letters here tell you to go the long way around. JKL, so that's 255 degrees, going the long way around. And then angle KOL, this central angle is the same as that intercepted arc, so that's that. This first one, find the values of x, y, and z. If this is a right angle, then it goes across. You can project it out to these endpoints here, and this is 180 degrees, so I can take away 65 and get y is equal to 115. Then if this is 80 degrees here, I can project out and get to this spot here and that spot there, and that's twice 80, or 160. And when I take away y, I can find this amount, and then I can add that to, let's see, the z amount. I want to do this in the right order, and get that angle y is, angle x right here. Sorry, this angle x, that's the one I should have started with. That's a right angle, apologies, because if this 90 degree goes to these 2 points, this one goes to the same 2 points. It doesn't matter that it's coming at it from the other side, because half of a circle is 180 degrees. So this side is 180, the other side is 180. They're always supplementary. These angles are always supplementary. So if we'd asked, this angle would be 100 degrees because it is supplementary with 80. And meanwhile, z then is 45 degrees is what this little arc CD is, and I take that away and cut it in half, and I get what z is. Z is also 45 degrees. And this problem here, if I know that this is 45 here, I track it out to where it hits the circle and I double it, that's 90. So that means that this angle here is the same, that's also 90. Then if this is 70 here and this arc hits the endpoints of this inscribed angle, it's half of 75, it's 35, and then because it's a triangle I can find that, add it up, subtract from 100, and I get 180, and I get 100 degrees. In the home stretch here, very quickly, an indirect proof for me would be extra credit. You just suppose the opposite and show that's ridiculous. In this case, if you assume that they are parallel, that's the opposite of what you're trying to prove. If they are parallel, corresponding angles would have these both be 90, but you're told that they're not 90. That's a very simple contradiction, therefore it is not true that they're parallel. Here, I think it helps to rewrite 2 as 1 and 1 over 1, and 1 and 1/2 is 1 and 1/2, 1 and 1/3, 1 and 1/4. You see the progression is 1 over n, and as n gets bigger and bigger and bigger, it goes to infinity. 1 over infinity is 0, so this has a limit of 1. This has no limit, it's just bouncing around, nothing there. The explicit formula, use your formula sheet. You see it's dropping by 3, that's the first term, that's the amount that it's dropping by, that's called the common difference, and then there's n minus 1. That's your explicit formula. You can plug in any value for n. I could go out to the 1000th term, plug in 1000, do the math, and I get the value. Here, this is being multiplied by 5, so I'm using my formula for the explicit terms of a geometric. There's my first term, there's my multiplier. They happen to be the same, so I can do the math and simplify it if I want, or you could write it like that. Here we have recursive formulas. Recursive formulas need starting numbers, they're called the seed numbers, and then a rule for how your little seed grows into a chain of numbers. In this case, you take any previous term and just add 0.11. Here you take, and you have to go back 3 terms, and whatever that term is, you multiply it by -1. So it's a bit unorthodox, but that's the way I did that one. Maybe Mr. Young has a different way. This one's a neither. The caret numbers give you neither a multiplier nor a common difference. This one has got a 5 that's being added each time, so this one is arithmetic. All right. Write the explicit formula. If you look at this carefully, the 2 is not changing. Down below it's multiplying by 3, so I simply put it over our explicit formula for a geometric like the other problem and simplified. That's all you got going there. You could have written it as 3 times 3 to the n minus 1 if you'd wanted to, but that's overcomplicating it. But that is the first term, and then that's the multiplier. Here we've got our first term, and we're adding on only 0.1 each time, and so this is our arithmetic explicit formula. This one's a little bit more involved because we're given a beginning term and an end term for an arithmetic. It's going down by 14, so we need to do some solving based on our nth term formula. This is the nth term, the last term. There's the first term, there's the common difference and our formula, and I just go carefully and solve. When I find out that it takes 20 jumps to get to our last term, I can plug that into the formula and solve for the total. This is the total amount then. And we're done.